Okay, hello everyone. So back in the physics lab, this is the first of the gas law experiments that I'm going to show you. I'm going to demonstrate how it works, then I'm going to go and collect some data and I'll share, and that will be shared with you via your online team system. So the first law, or the first relationship we're going to is after a guy called Charles Boyle, and it's called Boyle's law. And Boyle was investigating the relationship between the pressure that a gas is put under and the volume that that gas exists in. Okay, so this idea between pressure, volume, and you probably should, it probably makes sense to think if you put something under pressure, then the volume will generally decrease. Now solids and liquids, they don't tend to do that very much because there's not a lot of space for things to compress into, but a gas, loads of space between all the molecules, which means that, or the particles in the gas, which means that we have this ability to change. It's much more easy to compress, and we do that by exerting a pressure on it. At the moment, this is at air pressure. It's balanced, so what there is there's air basically going into this tube from the air around us, and it's exerting, inside here is a little hydraulic system. So we've got a little container of air, and that's pushing on a liquid, pushes up, and there's a pressure being pushed back by this column of air that's in here. So by forcing air into this container, we'll increase the pressure in there, which will transmit a pressure to the liquid. Pressure of the liquid will then make the liquid go up until it's balanced by an opposite pressure from the air in there. So that's how this system works. At the moment, this dial is at 1. It's 1 times 10 to the 5 pascals. So you probably can't see it, but that's what this little symbol here means. Essentially, that's air pressure. 100,000 newtons per square meter, or 100,000 pascals. And so what we're going to do, put the air in, and we will do this. So, connect up the spike pump, lock it so the air doesn't leak, valve is open, put some air in. Now you notice if I don't do anything, if I just then release it, it will then sort of push back because this pressure is now higher, so it's going to try and push air back out of the system, but I can close it by having that. But if I just leave it sort of open, we'll see a sort of decrease in the air pressure, and this volume goes back to what it originally was, about 44 centimetres from the top of that to there. So what we're going to do, put it back in again, lock it, okay, and then so what I have here, so I'm at about 2.5, so about 2.55 would be my best estimate reading this dial. So that's about 2.5 times atmospheric pressure, so that'd be 255,000 pascals, and my volume has decreased to, I would read that as being just about 17 centimetres. So that's about as accurate as I can be. And what I'm going to do, and I'll do this a bit later, you don't have to see me take all this data, is all I'm going to do is open the valve a little bit, let some air out, let these two values change and see what I get to. So if I open the valve a little bit, I then go down here, so I'm now at about 2.1 and about 20. Go down again, about 1.9. And I'm now at 21 to about 22.5. So I'm going to collect some data, and that'll be supplied with you, and we'll look to see what the relationship is between the pressure and the volume of a gas. Now there's a couple of assumptions that relate to this, that we're making two assumptions. One of them, perfectly fair assumption. One of them is that we're assuming that we haven't let any gas into or out of this column of air, which is true, otherwise it would not work. So there it's a fixed mass of gas. We're not allowing the mass of the gas to change. The second thing is that we're assuming that the temperature of this remains the same, because you might think when you heat up a hot air balloon, the volume of it increases and various things happen. We're saying the temperature doesn't change. Now that is not entirely accurate. It's an assumption. It's a perfectly fair assumption for this, but obviously as I push down this, I'm doing work. So I'm putting energy into this system. So it does increase in temperature a little bit. The formal way to get around that is that you set up your data, you set up your sort of system, and then you wait. You just wait for the temperature to equalize if there's been an increase in temperature. But various bits of the system will get hot. So normally what you then have to do is to wait a little bit to let the temperature cool down a bit. But on a scale of this, given the level of detail of accuracy with measurements we're taking here, the precision that we've got, that isn't going to really interfere with our results. So there we go. And so that will be the data that we'll use to investigate Boyle's law. Let's let the air out. That's satisfying.